Madeleine's going to talk to us today about Roman and the future of global cluster Asteroseismology. So this should be really exciting.
Hi everyone, my name is Madeleine McKenzie. I'm a Hubble Fellow at the Carnegie Observatories. Firstly, thank you for the opportunity to speak today, and also thank you to all the incredible people that have made Roman a reality. I'd like to talk about the future of globular cluster asteroseismology and all of the amazing things that Roman will do for this field, and highlight 47 Tuck as an excellent first science case. I'm here on behalf of Madeleine Howe, another Maddie from Australia, and she's the real driving the science behind all of this. So globular clusters connect the local universe and the high redshift universe. Here is just a timeline of the evolution of the universe, Big Bang towards me, present day on the other side of the room. And I've just put a couple of globular clusters kind of where they sit in redshift space. And as you would expect, globular clusters formed within the first couple billion years of the universe's evolution. And what's really cool about this is that JWST is unearthing these really weird structures that all kind of happened in this first epoch of the universe's evolution. This includes things like the nitrogen-rich galaxy GNZ11, these lens star clusters, the Firefly Sparkle, and some people recently have linked little red dots to potential globular cluster formation episodes. And so on top of this, globular clusters are excellent probes of stellar evolution. And so here is a JWST image of a globular cluster NGC 2808, and you can see this incredible substructure as you go down the main sequence. We can see these two different isochrone tracks, and these are representative of two different populations of stars. And so the main sequence and the turn-off stars gives us initial population differences, but we can also look at the evolved stars. So this is a different cluster, this is M4, and the red horizontal branch stars are in yellow, the pink stars are the early AGB, and the blue stars are the RGB. And these evolved phase give us a really deep insight into mass loss and general stellar evolution. And so, focusing on this again, we've got simulated Roman power spectra for stars that are along the RGB. So closer to me is the red horizontal branch power spectra, and further away is the blue, the RGB spectra. And in evolved stars, convection excites global oscillations. And so in each of these plots, frequency is on the x-axis, oscillation power is on the y, and we've got our simulated spectra. And this dashed line represents the point of maximum oscillation power, delta nu. And if we know the luminosity of our star, and we also know its temperature, we can derive an astroseismic mass for them. Trevor is going to talk more about asteroseismology later today, so I'm just going to focus on the things that mass can do for our globular cluster populations. Okay. This is that same cluster once again. On the x-axis is just Gaia colors, so as I go further away from me, we're getting to the brighter end of the cluster. And we can see that the mean mass decreases as you go from the lower RGB to above the RGB bump. The mass then decreases again on the horizontal branch, and then one more time on the early AGB. And so we can get seismic mass directly weighing these stars and telling us about integrated mass loss. What I'm really interested in particular is the connection between spectroscopy and asteroseismology, so chemoseismology maybe, and that's do chemically distinct populations have different masses, and do they experience different amounts of mass loss? And so I'm slowly collecting very high resolution spectra of these stars using the Carnegie Planet Finder spectrograph, and we're going to be talking about and trying to answer the question of connecting birth stellar chemistry to subsequent mass loss and evolution. And this is going to be a big feature in a couple of upcoming surveys. For example, the After Sloan 5 Atomic Genesis Explorer will be focusing on this kind of connection between asteroseismology and spectroscopy. So looking more to the big picture on global mass loss, on the x-axis I've got metallicity, and on the y-axis is the integrated mass loss. And as we can see, as we go from metal poor to metal rich populations through the globular clusters, we get this rise in the amount of mass loss. So the more metal rich you become, the more mass you're expected to lose as you go through those phases of evolution. But you see an opposite trend at the high metallicity end through open clusters and field stars. And so there's this critical region where more astroseismic measurements of metal-rich clusters are critical. 47 Tuc is an excellent example of where this fills in this gap here. We need to know whether this trend increases, whether it turns over, or whether it flattens down. And that's why I think 47 Tuc is the ideal test case for the first Roman globular cluster astroseismic fields. 47 Tuc, you can see the Roman footprint here goes across the cluster very nicely, and it's so much bigger than what we have for our existing HST in green and our JWST in red filters. There's also a huge amount of complementary optical, infrared, ultraviolet, X-ray, radio, and spectroscopic data available for 47 Tuc, so we can build this really comprehensive picture of what's happening in this cluster. The real power, I think, comes from the pixel size, the sampling. So Roman can separate stars that other time domain surveys just blend together. The TESS pixel is in red on the side, the Kepler pixel is the white pixel, and the Roman pixel is approximately really small and tiny on the screen. And when you compare that to the core of a globular cluster, this is a HST image, Roman is really the only thing that is going to be able to resolve a lot of those small stars. And everything, all the other previous surveys just blend it together. And so I want to put Roman in the context of all of the survey landscapes that we kind of have at the moment. Caveat, this is very biased, but I'm going to go through it anyway. So a lot of cluster science can be done with existing kind of facilities or very soon to be coming up facilities. So we can resolve cluster cores already with JWST and HST, and these two can actually reach down to very low mass stars. For example, JWST has gone all the way down to the brown dwarf sequence in 47 Tuc. Euclid and Rubin will map the wide tidal structure. JWST and Euclid can see through the bulge extinction in the more infrared filters. We've got wide field space-based imaging, so we're avoiding the atmosphere with Euclid and Plato. But JWST and HST can do time domain, but it's very small fields. And bright star astroseismology is where the Plato mission does shine, but Plato has much larger pixel sizes and cannot resolve cluster cores. And so it kind of leaves Roman in this space where it's the only thing that can do large-scale red giant astroseismology in crowded cluster cores, and this is unique to Roman. But unfortunately, the elephant in the room is the problem of saturation. And so recovering saturated giants unlocks, for me, very biased, the highest value science for this type of proposal. But you can see with these, the cyan lines, that's the saturation limit. And so on the color magnitude diagram plot, this is colored by the probability of seeing solar-like oscillations. And unfortunately, the vast majority of these stars are above this saturation limit. And on the right plot is showing a similar thing, showing how different baselines will impact your detection probability. And so all giants with the highest probability of solar-like oscillations will be saturated in a 66-second integration. And one solution, however, is halo photometry to extract non-saturated stars in the PSF wings rather than in the saturated core. So these stars are saturated, but they are not lost. And I hope a lot of work can hopefully go into doing this sort of thing so we can recover our astroseismic signals. And so briefly to kind of go to the conclusion of this talk, I wanted to highlight a couple of the extra bonus science cases you get by observing 47 Tuc. You can see 47 Tuc is really close in the plane of the sky to the small Magellanic Cloud. And so here's our color magnitude diagram with Tuc in red and the SMC in gold. And you won't be able to do astroseismology in that same kind of vein in the small Magellanic Cloud, but you will get incredible data from Cepheids, RR Lyraes, and long period and semi-regular variables to look through and mine in this sort of data set. And you also get to compare two very different populations across age and metallicity. For the planet people out there, Roman can test planet formation in 150,000 metal-poor alpha-enhanced stars. Globular clusters are generally thought to be quite not great for planets because of their low metallicity and the dynamic stellar environment, but I've been told there's a planet in M4 which orbits a pulsar and a white dwarf. And recently, a hot Jupiter was discovered at the metallicity of around 47 Tuc, which sets the precedence that we could get planets at this metallicity. And the other final thing is the exotic phenomena that you can find in 47 Tuc. So you can see that the number of X-ray binaries increases as a function of stellar encounter rate, and 47 Tuc is really one of those highest number of X-ray binaries that we have. We've got Hubble fields, we've got with cataclysmic variables where we can see between the different Hubble epochs this variable popping out. And 47 Tuc is home to X9, which I'm told is the only known ultra-compact black hole white dwarf binary in the Milky Way. And through ATCA radio imaging, there's millisecond pulsars, or this thing could be a weekly accreting black hole. I think this was 400 hours of ATCA imaging. And so we're going to have a plethora of observations. They're going to be UV, time domain, HST observations of the core, and they're all going to be synergistic with one another to tell us about all of the incredible things that we can find in these star clusters. And so just to conclude here, 47 Tuc fills this key gap in the metallicity dependency of RGB mass loss, and seismic masses can test whether the low metallicity trends, flattens, or turns over in this picture. And chemoseismic analysis connects stellar mass and evolutionary state to the chemical composition. Of course, the saturated sources need to be fixed and find a solution for that, but I'm hoping that smart people in this room will be able to solve that one. People who have relevant topics to all of these are their emails, and so I'll just leave it there. Thank you so much, everyone.
I guess I should be on this side so I can get in the video, I guess. But what kind of questions do we have for Madeleine? That's a great talk. Thank you. Yes, Ryan?
Yeah, thanks for the nice talk, Maddie. I guess I have a quick question about the halo photometry. So does that impact you can resolve sources in crowded fields?
I am a simple-minded spectroscopist. I can direct you to Maddie, the other Maddie, the Asteroseismology Maddie. And I think there's someone with a poster here as well who might have more information about that.
Okay, thanks.
Okay. You have a question up there?
Yeah, great talk.
I just was curious, you mentioned at one point there were 3 different isotopes of magnesium. I'm really new to this. Can you tell us what that was trying to tell us?
Yes, thank you. It's almost like I planted this question, but I didn't. So I am not an astroseismologist, to be clear. I am a spectroscopist. I use incredibly high resolution instruments, so that's why I usually piggyback off the radial planet spectrographs. And so I measure individual isotopes of magnesium in stars to link that to the different chemical evolution pathways that a star forms. And so the spectra that I was just showing here, thank you so much for picking up on it, is this really, really new stuff that I've collected since arriving at Carnegie. And because of the low vibrational energy transitions within a magnesium hydride molecule, you see that splitting and you can measure it and recover it in stars. And so there is a relationship between things that have more magnesium 25 and 26. We think they have more mass loss because they have higher helium, which affects the evolutionary of the star. And so it's a really big complex picture, but everything is kind of falling into place very nicely. Thank you.
Okay, so then we'll move to our next speaker. Thank you so much, Madeleine.
Thank you. Thanks for having me.